So in the last slide, in the last set of slides, we looked at an inductor that had an input on one end and was grounded on the other end. You might imagine that we would like to have an inductor that was a floating inductor. In other words, one that we could connect a circuit to either end. So one that we could put an input on one end and take an output on the other end, for instance. And in order to do this, we could use a fully differential circuit. So for instance, we could make a transconductor that was fully differential, and that might look as follows. So here we have a GM1, and we have some kind of current source inside this that represents our transconductance. This is dependent upon the voltage at the input, and it would be a differential voltage at the input. We use another transconductor to feed back a signal to the input. Where here, again, we have some kind of differential transconductance dependent upon a differential voltage at the input. So here we might put a test voltage source, Vx, into the circuit and measure the current Ix flowing into the circuit. Let's connect this in the opposite polarity. Here we have a current Ix flowing this way into the circuit. All right. So here we have two capacitors equal to C that are connected similarly to the way they were for the single-ended circuit. And we have our feedback circuit connected as is drawn here. Alright, let's label this node X minus and this node X plus, and we'll label this node Y minus and this node Y plus. Now we can write that Vy plus is equal to minus big GM1 divided by SC times Vx plus minus Vx minus. We can say Vy minus is equal to GM1 divided by SC times Vx plus minus Vx minus. Now, similarly to what we said before, we can say that this feedback current that we'll call I.O. is equal to minus Ix. So we can say that I.O. is equal to GM2 times Vy plus minus Vy minus. And hence we can say Ix is equal to 2 times GM1 times GM2 divided by SC times Vx plus minus Vx minus. So we could find Vx plus minus Vx minus over Ix would be equal to the input impedance to the circuit, which is equal to S times C divided by 2 times GM1 times GM2. Again, this represents a floating inductance now, where we have an input terminal we would call X plus and X minus based on the way that we've just drawn things for the circuit above. And this inductance would be equal to C divided by 2 times GM1 times GM2. Alright, so now we see how we can make a floating inductor out of this circuit. Alright, and the next set of slides for this lecture, we'll look at what happens if our transconductor is not ideal. And what we're particularly going to look at is what if our transconductor has a finite output resistance. In other words, the current source associated with the transconductor has some loss associated with it.